In this video, we'll look at what is interference and what is two-source interference. There are quite many learning outcomes here, so this video is quite long. So let's just zoom in straight away to what is interference. In previous lecture, we have looked at what is superposition and what is meant by coherent. So here it is just a build-up, right? So interference refers to the superposition of coherent waves which result in change in overall intensity. Right, let's look at two types of interference. The first type is called constructive interference. Right, this means when we have two or more coherent sources, they arrive at a point in phase, which means the phase difference is zero. These individual waves will reinforce each other, right, and the individual displacement will add up, right? That is our principle of superposition. Therefore, the resultant wave amplitude will become sum of the amplitude of individual waves, so it becomes larger. This will give us a resultant wave of maximum amplitude and intensity. Right, so for example, wave X and wave Y meet at point P. So the resultant will be a wave Z. So this coherent wave, a point of constructive interference will vary with time. Right, you can see that sometimes it is a maximum, positive maximum, and it can decrease and becomes a negative maximum displacement, right? So the displacement will vary with time. And there is no point of permanent maximum displacement, which means it will not always be at the peak, but instead it will vary. And this point will give us maximum amplitude and maximum intensity of the wave. Right, therefore, the light will become brighter if we are talking about light waves, and the sound wave at a point where they constructively interfere, it will be louder. And same thing for water wave, you will get a higher crest or deeper trough. In contrast, if we look at the second type of interference, which we call destructive interference or DI, these two or more coherent waves, they arrive at a point anti-phase. So anti-phase is not the same as out of phase. Out of phase means not in phase, right? This is not in phase. But anti-phase means the phase difference must be pi. Individual waves will cancel each other, either partially or totally, right? So the resultant wave will be a minimum amplitude and intensity, right? If we again look at wave X and wave Y, if they meet at this point P, the resultant will give us a wave Z. Right, in this case, you can see that they totally cancel out each other. Right, and there will be a point of minimum displacement. In this case, the displacement is zero because it cancels out. And so at point P, it will always be zero for this case. Right, and it's zero because the amplitude are equal, therefore they cancel out totally. Okay, in the case where amplitude are not equal, then it may give us something like this. Right, so instead of one straight line. In this case, we'll get a light that is dimmer or no light if there's destructive interference, or sound that's softer or no sound, where if the amplitude are the same and they totally cancel out each other. Okay, we may be thinking, quite strange, right? If I shine two light waves, right, I'm supposed to get a brighter light, but how come it can actually cancel out, become dimmer or no light? Yes, so this is the interesting thing about interference, right? So it is not always becoming brighter, it can also become dimmer. So when does a constructive interference occur? Right, for example, we have one slit here, right, and we have a wave that passes through this. You can imagine this to be water waves, right? As water passes through this small slit, it is going to diffract, right? And as it diffracts, it becomes a circular wave. And this circular wave will reach two more slits. This is what we call like a secondary source. And in turn, each of these circular wave will be diffracted again, and they form two sources of waves, right? Which is why we call this the secondary source or sources. Okay, so if we have a point P, right, which is a distance of L1 away from S2 and L2 from S1, right, we can call this the path length, okay, or simply the path distance. This is actually just the distance. Okay, so if we want to know when constructive interference occur, we can look at this, the path length. Okay, so we will look at the difference in path length, which we will call it a path difference. So for example, from S2 to P, the path length is 6 lambda. Okay, so 6 wavelength, you can see 1 wavelength, 2 wavelength, 3 wavelength, right? 1, 2, 3, 4 wavelength, 5 wavelength, 6 wavelength. Like similarly for the from S1, right, we have 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6 wavelength. So you notice when the crest meet with crest, it will give us a constructive interference, right? Because they arrive in phase. The path difference is actually 6 lambda minus 6 lambda, so we get 0 lambda or 0. Let's look at another example. Right, in this case now, we have a 1, 2, 3, 4, 5, 6, 7 for the blue waves. 1, 2, 3, 4, 5, 6 for the black waves. Right, what is the path difference? It will be just 7 minus 6, so it's equals to lambda. Right, again, it is crest meet crest, right? Okay, so therefore it is constructive interference again. Okay, let's look at another example. Let's say now I have 1, 2, 3, 4, 5, 6. Okay, 6.5 for the black wave. 1, 2, 3, 4, 5, 6, 7, 7.5. So the path length is 6, 7.5, and 6.5. So the path difference will be 1 lambda again, right? Because it's 1 lambda, now it will be trough meets a trough. Okay, in this case. So whenever we have two sources that are in phase, right? If you move back, you can see that they are in phase. They start off both at the crest, right? The path difference, if it is integer of lambda 0, 1, 2, 3, right? Or we simply call it n lambda, where n is 0, 1, 2, 3, 4, 5, 6, etc., or a whole number integer, right? When the path difference is n lambda, we will get constructive interference. Let's now look at when does destructive interference occur. Okay, I'm sure you have an idea now. Again, we have a single slit and 2 slits here, right? And then with a wave passing through. Right, so now at point P, if we want destructive interference, how will it be? So again, we use the path difference, right? Notice again, we both start from the crest. Let's look at the red one. So 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 lambda for the red wave. 1, 2, 3, 4, 5, 6, 6.5 for the black lambda, black wave. Okay, so the path difference will be simply 7 lambda minus 6.5 lambda, so we get half a lambda. So this will allow us to have the trough meeting the crest. So for destructive interference, if the two sources are in phase, the path difference, so long it is always half a lambda difference, okay? So we have n is 0, 1, 2, 3, 4, 5, right? So it can be 1.5, 2.5, 3.5, or just half, right? Or 4.5, so on and so forth. Right, so long we have a path difference that is n plus half times lambda, we will get a destructive interference. Okay, remember this is for sources that are in phase. What about sources that are anti-phase? If they are anti-phase, let's look at it now. For example, this start with a trough, right? This start with a crest. So they are anti-phase. So let's count how many lambda. 1, 2, 3, 4, 5, 6, 6.5 lambda. 1, 2, 3, 4, 5, 6, and 6 lambda for the black wave. So in the end, we are going to get half lambda, right? So half lambda, but in this case, it is crest mid crest, right? So if crest mid crest, we are supposed to have constructive interference. So although the difference is half lambda, it is not a DI because this is anti-phase. Okay, the sources start with anti-phase, right? One start with crest, one start with trough, right? Okay, let's look at the next one. So if these two, again, one start with crest, one start with trough, and they are anti-phase, you'll find that they will meet anti-phase, okay, if these two path lengths are the same. So therefore, the path difference in this case is 0, right? When the path difference is 0, they actually crest meet the trough, so which will give us a destructive interference. So therefore, when a path difference is n lambda, we get destructive interference. This is for anti-phase. Okay. Right. So just a quick recap. For two sources in phase, if we want constructive interference, the path difference should be n lambda. If you have one destructive interference, the path difference should be n plus half lambda. But if the two sources are anti-phase, then it will be the reverse. Now let's look at example 1. Okay, we have two narrow slit S1, S2, right? And they are not same distance from the point S, so L1, L2 are not equal. If the light is allowed to fall on the screen, state the condition for destructive interference at P. So we want a destructive interference at P. Okay, so if we look at the table earlier, which one would we use? Okay, we can't use any of this because we don't know these two sources, whether they are in phase or anti-phase, right? So what can we do? But we know they will be in phase from this point S, right? So we should be looking at the path different from point S. Okay, in other words, I should look at the path traveled by one wave, which is L1 plus L3, and minus the path traveled by the other wave, which is L2 plus L4. So the path difference should be equal to n plus half lambda, okay, because they start off in phase here, right? Therefore, in phase, we should use n plus half lambda. So this is for destructive interference at P. Just now we are looking at path difference, so now we'll look at phase difference. Okay, phase difference at a point equals to the difference in phase at that point, okay, at that point. So it is regardless of how the source start with, okay, whether they are in phase or out of phase or anti-phase, we don't care. We just want to look at the phase at that point where they meet. For constructive interference to occur at P, where they meet, the phase difference must be n times 2 pi. That means n can be 0, right? So there is no path, no phase difference when they meet. Okay, or they can be 2 pi radian for the phase difference. Okay, for destructive interference, of course, it will be a odd number. So even number if it's constructive interference, odd number for destructive interference. Okay, in summary, if we look at two sources that are in phase, the path difference should be n lambda to give us constructive interference and n plus half lambda for disruptive interference. Okay, and for anti-phase, it will be the reverse. What about the phase difference? Okay, the phase difference for constructive interference, whereas in phase, it will be n times 2 pi. And for disruptive interference will be n plus half pi. Now you look at it, for antiphase, it is exactly the same. Okay, therefore really it is regardless of the sources. You just look at the point they meet, whether they are in phase or not. All right, that is the main thing you must take note. Okay, we have finished that section. Now let's look at the new section. For interference pattern to be observable, it means it must be well defined. We can see it clearly. The waves must be coherent. They have about the same amplitude, right? If it's equal, it's the best, so they can cancel each other. And they should be polarized in the same plane, okay, or unpolarized, right? And of course, they should superpose. What if the two waves are not coherent? Okay, look at this GIF. The black wave is actually the resultant wave. So the green wave and the blue wave, they are always superposing, right? And you can see that now the black was constructive and now it is destructive. In other words, the resultant wave is always changing. It is sometimes constructive, sometimes destructive. As such, you cannot see that they will totally cancel each other at all times, or they will not add together at all times. Back to this GIF where we saw earlier, right? You can notice that there are lines that are no waves at all, okay? So in this case, you can see the red lines that I draw. There are no waves at the red lines. If you can't see that clearly, you can see it here now. We have two dipper, right, and it's oscillating. So this is a water, right? As you can see, you will see these dark lines. So this is where disruptive interference occur. If we look at microwaves, right, it's the same setup, so that we have two secondary waves here, and then they will diffract, right? And we will have a detector that moves up and down, right, and to detect whether it's constructive or destructive interference. Let's look at a video to understand better. Okay, so we have two microwave emitter and we have a receiver. This receiver is connected to a CRO or oscilloscope and also connected to a receiver, a speaker, so you can hear the sound. Right, as we move the receiver along side to side, you can hear the sound changes in volume, right? Sometimes louder, sometimes softer. So when it's loud, is it constructive or destructive interference? When you can't hear anything, is it constructive or destructive interference? Let's look at the CRO. Okay, so the received wave, you can see, is changing. So this is constructive interference and now destructive interference, constructive and destructive. So as you move the receiver side to side, right, at some point it's constructive interference, some point it's destructive interference. Okay, constructive interference, destructive interference. Now let's look at the calculation part. Now we will learn a new equation and we'll use this equation to solve problems. Okay, another two-source interference example is the Young double slit. Okay, this is used for light waves. So we have a monochromatic light source. Chromatic means frequency, so monochromatic means single frequency. So actually it's one color, right? And then you have this has this single slit, okay? And then we have two secondary source here, a double slit. Right, so this is to ensure that they are in phase and we have two sources so that they can interfere. Right, and on the screen, okay, this is the screen. When we look at the front view, you will see this. You see bright and dark lines. Okay, the bright lines represent the constructive interference, the dark lines represent the destructive interference. Okay, so this is something like this, okay, that happens here. Right, so again, you can see the dark lines here, the destructive interference. So the narrow slit, as I mentioned, they act like sources of waves. The waves emerging from slit original from same wavelength, so they started from here, so they have the same wavelength and they are in phase because this distance is the same. Okay, right, and now these two sources will interfere or superpose with one another. You can see that this part is the constructive interference, this part is the destructive. Okay, so maximum is constructive, minimum is destructive. Let's look at that in detail. Okay, for any point on the screen, called point P, right, since the sources are in phase and they are from the same wavefront, right? Same wavefront means this, they are from the same wavefront. Okay, so same wavefront, definitely they are in phase. These two waves travel the same distance, so this distance and this distance is the same. They will arrive in phase. Okay, so the crest meet crest and trough meet trough. And therefore constructive interference occur at the center point. Okay. Now, if we look at point Q, right, S1 has to travel further. This is a longer distance compared to this S2Q. And it happens to be one wavelength further. So therefore, they will still arrive in phase. And therefore, this is still a constructive interference. Okay, now what about in between the two bright spots or 2 points of constructive interference? In this case here, this S1R is 1/2 of the wavelength longer than this path here. So therefore, they must meet antiphase because the path difference is half lambda. So this will be a destructive interference. Okay, let's look at in detail this. Again, we have the source, right? And then from the same wavefront, so it reach here, same wavefront. So these two will be in phase. Right, and S1, S2 become two sources that are in phase. Let's look at point P. This S1, the wave from S1 will travel exactly same distance as from S2. Right, so the path difference is 0. Therefore, this will be a bright spot of constructive interference. Okay, this is what we call the central fringe. Now let's look at another point, point K here. Right, this is a crest and dotted line are the trough, right? So you can see the crest meet with a trough of S2, the crest meet with the trough of S2. So you join up all these points where the crest meet the trough, crest meet the trough. You join up this point, you get this line. Okay, here also the crest meet the trough, you get this line. So this is a line where there is destructive interference. Okay, so at this point, actually it will be always destructive interference, right? And the path difference is half a lambda. Okay, so therefore you see a destructive interference here, a dark fringe. Let's look at L. L, it will be, you can see if I draw all the crest meet crest line and trough meet cross trough line, I get this. Okay, so this whole line, you will get constructive interference. So at this point, it is also constructive interference. and the path difference is 1 lambda. Similarly for M, you can see the path difference is half a lambda, therefore it must be disruptive interference, so a dark fringe. And here, constructive interference, where path difference is 1 lambda, so this is a bright fringe. The center part is a bright, so there's constructive interference, and the dark spot is a disruptive interference. If why it appear red color, this is obviously because we use a red light. Okay, now let's look at the intensity graph. Okay, as this is the shortest distance, right? So the intensity should be brighter, right? Remember, intensity is higher when the distance is shorter. But in this intensity graph is drawn like this, but actually normally the intensity is really almost the same. Sorry, it's almost the same as the peak. Why? Because the distance is actually not too far away. Right, remember we are talking about light waves, and this distance is really very small, so the intensity is really quite close. Right, so in exam you should draw them to be equal for a young double slit. Okay, so it should look something like this. All right, so now let's look at the formula already. So if I want to find the distance between the two bright fringes, okay, the two maximum point here, we call this distance x, okay, and x is called the fringe separation. So it is a center of this fringe to a center of this fringe, or center of this fringe, center of this fringe. So actually, x is equal, all right, it is like a zebra crossing. Bright dark, bright dark, bright dark. So the formula is given by this, x equals to lambda d over a. Lambda is of course the wavelength of this light, and d is the distance from the slit to the screen. So this is d, and a is the distance between the two slits. Okay, so you get distance between the two slits, that is your a. Okay, a few things you need to take note about this formula. Right, it is only applicable to interference of light if d is much larger than a. That means the distance from the slit to the screen is much larger than the distance between the two slits. And it is not applicable for microwave, sound wave, or water waves. Therefore, if you have a question that involves microwaves or water waves, right, you are not allowed to use this formula. So what can you do? You will use path difference. Only when the path difference cannot be used, then you assume that this equation can be used. Okay, so I repeat again, if it's not light and not this condition, you should use path difference. Only when path difference cannot be used, then you will use this formula. Most of the time we use monochromatic light. This can be achieved by passing white light through a filter. So for example, you want red light, you use a red filter. Now with the invention of laser, we can actually shine the laser beam directly on the double slit. Okay, previously we will need this slit, right? So you need one source here. Okay, but because laser itself is coherent and monochromatic, so you can actually use a laser and you can use a double slit straight away. If you are interested in the derivation, you can look at page 32 in Appendix A. In this example, we have coherent red light emitted from two parallel narrow slits which are 1 mm apart. So this is my A. Determine the distance between the central bright fringe and the dark fringe. Okay, if the screen is 1 meter away, so there's D. And lambda is also given. Right, so if we look at the central bright fringe, it will be this, right? And the third dark fringe will be here. So in total, this will be 2.5 x. Okay. So using the formula, let's find x first. Substitute lambda 700 nanometers. Get this. And d is 1 meter and a is 1 mm. Right. So you can find x and since we know the distance between the central bright fringe and third dark fringe is 2.5x, we can find very easily. Young double slit experiment. A small detector measure intensity of illumination of X unit. So this is the intensity at the central bright fringe. In one of the two identical slit is now covered, what will be measured? If we have a double slit and you cover one slit, what will happen? Okay, so if there's only one slit, there cannot be a double slit interference pattern, right? Okay, so there is no bright and dark fringes. So in other words, how can we measure the intensity of one single light? Let the amplitude be A. If both slits are open, resultant amplitude should be A plus A, right? This is from superposition, principle of superposition. So the resultant amplitude is 2A. And remember, since intensity is proportional to amplitude square, right? So it should be proportional to 2A square, therefore 4A square. If we cover one slit, then the amplitude is only A, right? Therefore, intensity is A square. So A square should be 1/4 of X. Okay, that's how we solve the question. Work example 4. You're given intensity of wave A and intensity of wave B. If these two interfere constructively at a point, what is the intensity of resultant wave? Please note that you cannot add up the intensity. Okay, we must always add the amplitude and then find the intensity of the resultant amplitude. So from intensity is proportional to A square, we can find that the amplitude is proportional to square root of 1. Okay, this is wave A. And for wave B is square root of 2. Therefore, we should now add up the individual amplitude since this is constructive interference. Okay, so for constructive interference, you add this up and the intensity, you just square the amplitude. You will get this. Right, and to find for destructive interference, you will subtract, right? So we put a modular sign because amplitude should be a positive number. Okay, so it doesn't matter which minus which once you put a modular sign. So resultant intensity will be 0.172. Okay, now let's look at example 5. So again, we have a coherent light. So this is likely from a laser and then with a double slit here. Okay, so you are given B, you are given A. Assume the fringes near point P on the screen reaching from slit A alone has intensity I and from slit B alone has intensity 1/3 I. Point P is equidistant from two slits. Determine the intensity of the bright fringe at P and the dark fringe near P. Okay, so again, should we do a vector sum of the intensity? The answer is no, right? We can only do a vector sum of amplitude and find the intensity from resultant amplitude. So like work example 4, this is what we need to do. So when constructive interference occurs, you add up the amplitude and then you square it. Okay, for disruptive interference, you subtract it. Again, it's a modular sign here. And then you square it. Okay, so you get the answer. Right, now test yourself. Describe the fringe pattern of a young double slit experiment. So how do you describe this? First, you'll say standard bright and dark fringes. Equal distance between each fringe, right? So here to here is X. Here to here is also X. Next question. How can we make the central fringe to be a dark fringe? Now you can see that this is a bright fringe. How do we make it a dark fringe? Actually quite easy. We just make S1, S2 antiphase. So we can make them antiphase by placing a single source nearer to 1, something like that, such that they will be half lambda apart. Okay, or n plus half lambda apart. So from here you get antiphase sources. This is the end of the lecture. So test yourself. Again, are you able to do all this?